Okay, here we go, the last bits of BC Calc. So in the last section of BC Calc, we have to talk about functions that are defined parametrically and functions that are defined in polar coordinates. Now, you did parametric and polar coordinates in pre-calc. You did. But not everybody always remembers them. So the good news is we don't have to do a whole heck of a lot. We have to be able to take derivatives of them. So do things like find horizontal and vertical tangents based on that derivative, which isn't too bad. We use parametrics for motion problems, and then we have to learn how to take the area inside polar graphs. If you remember polar graphs, they're those like loop-de-loop ones, the rose curves and all that good stuff. So none of that is particularly difficult. We just have to memorize some formulas mostly. Okay, so let's get started. We're going to look at parametrics first. Okay, so when we look at parametric functions, we know that time in parametrics is introduced as a third variable. So what we see when we see a parametrically defined function is two equations. We see x and we see y, both defined in terms of t. So again, when you see a parametric, you don't see one equation, you see two. So here I can move my head out of the way. Here we go. This is one function defined parametrically. So they're telling us at any given time t, x will be your t-value minus 5. In other words, that's its position horizontally. This is its position vertically. So when we plot points for parametrics, we start with a time, and from the time we get our x and y coordinate, and we plot that point. What's interesting about parametrics is that the t-value, the time, doesn't show up in the graph. We're still graphing on an xy plane. Okay, so let me show you what I mean by that. All right, so if we make a table of values over here, let's start at time equals 0 because that's a reasonable time. Right? At t equals 0, the position of this thing should be 0 minus 5 or negative 5, and let's see, 0 minus 9. Okay, so that means that the path of this particle begins at negative 5, negative 9. So right there. And then I can follow the path of this thing by plugging in more and more times. So 1 minus 5 is going to be negative 4. And then let's see, 0.5 minus 9, so negative 8.5. So it hasn't moved a heck of a lot, huh? So negative 4. Something like that. Yep. As time gets bigger and bigger, as time goes on, this is going to keep moving. So right, I know what my x is going to do. Down here, this would be 4 times a half, so 2 minus 9. Now I'm at negative 7. So at negative 3, I'm at negative 7. And I can just keep going and going and going. And what I'm doing, I like to put little arrows on it, is sketching the path of my particle or my object or whatever it may be, right? Let's do one more just for fun, then we'll take a look at the curve. At 3 seconds, I should be at negative 2, then 9, so what, 4.5? Negative 4.5. So, did I? Oh, you see what I just did there? I got lost. I started looking for negative 3. The time isn't on the graph. Negative 2 is where I need to be, negative 4.5. So there's negative 4. All right, something like that. So again, my curve is continuing up this way. And you just keep plotting points, pick a time, plot its location. And I think that for me, the arrows help me remember what I'm doing here, right? This is not just any old curve. This is the path of a function over, the path of an object over some time. So there's my curve. I did a pretty darn good job of plotting my points there, if I do say so myself. And if I kept going, I would see that continuation. Okay, so that's a parametric function. That's how they're defined. Now, obviously, there was no calculus there. Right? That was the pre-calc part. So here comes the calculus. Okay. Parametrics and vectors go hand in hand. So if you're in physics, you're used to vector notation. If you are not in physics, let me just show you. It's not a new concept. It's just a new notation. Okay. When we talk about parametric form, again, we see two equations, one for x and one for y. Vectors when you write a function in vector form, you're doing the exact same thing. You're breaking it into two components, an x component and a y component. So we're saying, okay, here's the horizontal piece of this function and here's the vertical piece of this function. That's really handy in physics, right? Because especially with projectile motion, when you're moving up and down, you've got gravity to contend with. When you're moving back and forth, you don't, right? So it's really helpful to be able to separate the horizontal motion from the vertical motion. So all vector form is a different way of writing parametrics. So if I'm writing it in vector form, one of the ways we can write it is with these, that's the greater than or less than signs, right? I call them pointy brackets. So all you're going to do is you're going to put your x component first and your y component second, literally just like you're writing a coordinate, right? But instead of parentheses, pointy brackets. So that's letting us know, look, these are the two components of a vector. So I could rewrite a parametric function like this by just putting my two expressions in the pointy brackets. So there's the parametric function we just looked at. We wrote t minus 5 is my x component, 0.5 t squared minus 9 is my y component. I just put them in the pointy brackets separated by a comma. It's just a different way of writing it. If you see this notation, it means this. You got an x component, you got a y component. Another way of writing it, which looks a little more scary, but it's not, again, it's just different notation, is what we call IJK notation. Now, IJK notation is, again, used a lot more in physics, but I have seen it pop up on the AP here and there. And again, it's just notation that you need to recognize. These are what we call unit vectors. So they are exactly 1 unit long and they are in a certain direction. This is a unit vector in the x direction. And this is a unit vector in the y direction. I don't know why they used I and j. I don't know. In physics, when you add the third dimension, it's k, right? K is your z coming out. So they call it IJK. But again, you can remember that it's vector because this is read sometimes I hat, which I think is kind of funny. It's supposed to be a hat, but it's the same symbol as you're using on your vector formats right here, which, by the way, just happens to look like a V. Coincidence? Maybe. So if I want to write my vector in that form, all I have to do is write my two expressions and then put i's and j's after them. Right? So again, up here, instead of writing x of t equals, I'm just going to put that expression with the I hat next to it, and then plus my y expression, j hat. This is saying the x piece of this function is t minus 5, the y piece of this function is 0.5 t squared minus 9. So we've got 3 different ways of writing the same exact thing. This they call parametric form, this they call vector form. It's the same idea. It's a function that is dependent on time, and we define our x value and our y value separately. So you plug in a time, you get a coordinate. You don't get a single number. You get a coordinate. You get a location. All right. So calculus. I believe we did derivatives of parametrics way back when we were learning to take derivatives, but in my experience, when I say that, everybody says, no, we didn't. So if you take the derivative of anything in vector form, because it is written in its component form, we have to be a little clever. Okay. So first things first, we need to know when the derivative exists. The derivative is going to exist if the derivative of the x piece and the y piece both exist. So remember, you can't have in a regular function defined in Cartesian coordinates, if there's a derivative, or I'm sorry, if there's a 0 in the denominator, or if you have a corner or a cusp or something like that, we would say the derivative fails to exist. If you want to know if a parametric or a vector derivative fails to exist, you have to look at both of its pieces, right? If either one of them has a corner, a cusp, a vertical tangent, a discontinuity, then the derivative overall doesn't exist. We just have to look at both components now. Okay. And we call it differentiable if it has a derivative for all of the t values, right? Before it was like if there's a y value for every x. Now I need an xy value for every t value. So they're going to give us an interval of time. They're going to say look at this object from time is 0 to 6 seconds, right? We're going to call it differentiable if it's got a coordinate everywhere between 0 and 6 seconds. If it doesn't, if there's a discontinuity anywhere in that time interval, then we say it's not differentiable there. And it's a smooth curve if and we talked about smooth curves before, this is not a topic that comes up a lot, if your derivatives are both continuous and never 0 at the same time. Remember, a 0 in the numerator is a horizontal tangent, a 0 in the denominator would be a vertical tangent. If they're 0 at the same time, we got a problem, right? That's a place where the derivative is going to fail to exist. So we say we have a smooth curve if our derivatives are continuous, no discontinuities. Okay, so let's try taking a derivative. Again, nothing new. All we have to do is memorize a formula. If I want to get the derivative dy dx, I just have to take the derivatives of my components individually and divide them out. So you can see here what algebraically happens. If you have dy dt over dx dt, the dt's just cancel. Right? All we're doing is manipulating it algebraically. So if I want to get dy dx, I'm going to take dy dt, which will be just t, over dx dt, which will just be 1. And we find out very simply here that our derivative is equal to t. So at t equals 1, my derivative is 1. At t equals 2, my derivative is 2. So the slope is going with the time. It's important to note here that my dy dx is in terms of t, and that's normal. It should be. If you're working in parametrics, the variable should be a t. Okay. Again, with more fun. You may remember when we did applications of integrals, we did the length of a curve. And our length of curve formula was 1 plus the derivative squared, right? dy dx squared. That changes slightly for parametrics because we have an x component and a y component. So what you don't do is take your components, find dy dx, and square it. But look at this. This is actually just the Pythagorean theorem in itty-bitty form, right? This is your change in x squared. This is your change in y squared. This is x squared plus y squared, right? And then we add them up and take the square root. So if I have a point here and a point here, and I want this length, I'm going to find my change in x and my change in y. I'm going to square them, add them up, take the square root. This is the Pythagorean theorem in infinitely small form. That's all it is. And if you remember when we did the length of the curve in Cartesian coordinates, we started with the Pythagorean theorem and developed it from there. So for parametrics and vectors, it's just a slightly different formula for length of a curve. You can use this to find, they'll ask you to find perimeters, right? You need to find the length of a curve. So here's a function here. We've got x is cosine cubed, y is sine cubed, and we want to find the length of that curve between 0 and 2 pi. So in order to do that, we need our dx dt and our dy dt. So dx dt is going to be 3 cosine squared of t. I tried. I can't do it. I have to rewrite it like that. 3 cosine of t quantity squared, chain rule, negative sine t. And my dy dt, if I don't rewrite it like this, I almost consistently forget to chain rule. I don't know why. You'd think I'd have figured it out by now. So I've got a 3 sine t squared, derivative sine is cosine. So here I have 3 sine squared t cosine t. So if I want to find my length from 0 to 2 pi, square root of dx dt squared. So that's 9 cosine 4th sine squared plus this guy, 9 sine to the 4th cosine squared. That looks like a fun integral to do. Now remember, there is some stuff you can do to simplify here, but you don't really need to, right? You could factor out a 9 and pull it out as a 3. You could factor out a sine squared and pull that out as a sine. And you could factor out a cosine squared and pull that out as a cosine. And then look what you have left. If you take a 9, a sine squared, and a cosine squared out of here, you're left with a cosine squared. And over here, 9, a cosine squared, and a sine squared, you're left with a sine squared. That's 1. So that whole thing, this whole mess, simplifies down quite nicely. So if you do a little bit of simplification, it's easier to type into your calculator. But you may prefer just to type it into your calculator. If all AP says is write the integral, I would stop right there. I'm not doing anything to it. If all they want me to do is write the integral, I'm done. If I have to type it into my calculator or do something with it, I might do a little simplifying. And again, remember, as long as you can factor something out, you can pull it out of the square root if you take its square root. Okay, so there's my length of that curve. All I gotta do is pop that into my calculator. All right, so for parametrics, we want to be able to take their derivative. We want to be able to find the length of their curves. Okay, so let's take a look at a problem that asks us to do all those good things. Okay, so number 1, it says rewrite the parametric in both vector format. So I want to write it with my little pointy brackets. So t squared minus 5, 2 sine t. And I also want to write it in ijk, so I will write t squared minus 5i plus 2 sine t j. In 1, 2, 3. 3 ways to look at it. If I want to find the derivative, I need to take dx dt over dy dt. Why do I feel like I'm not going to have enough space? Oh, I'm sorry, I did it upside down. Oh, whoa. Well, sorry about that. That was horrifying. I just wanted my eraser. Gosh. Oh my goodness. Okay, like I was saying, if I can do my derivatives correctly, dy dt over dx dt, right? Because I want to cancel out my dt's and get dy dx. So my dy dt is just going to be 2 cosine over my dx dt, which is going to be 2t. And there's my derivative. Okay, now, we did this back in the day, but again, just a little reminder, if you're doing a second derivative, what you have right here is dy dx, but it's in terms of t. So when you take the derivative, remember you're taking the derivative of this with respect to time, right? So you may remember there's a little trick to this, right? When I take the derivative of dy dx with respect to time, I have to use the quotient rule here, right? So denominator, derivative of numerator. Man, I wish I had more space. Negative 2 sine t. I can't do it. I gotta do it down here. So denominator, so 2t, derivative of numerator. So the derivative of 2 cosine t would be negative 2 sine t minus numerator, derivative of denominator, all over denominator squared. So 2t, quantity squared. All right, let's see. This becomes negative 4t sine t minus 2 cosine t all over 4t squared. You can cancel out a 2 if you want. It's really not that exciting. Here's the problem. This isn't d squared y dx squared. What we have is I took the derivative of y twice, but the first time I did it, it's in terms of x. The second time I did it, it was in terms of t. So if you remember, there's a quick fix for this, right? I need this dt to turn into a dx. So all I do is I multiply by dt over dx so that my dt's will cancel. Multiplying by dt over dx is the same as dividing by dx dt, right? So all I have to do is take this and divide it by dx dt. In other words, throw a dx dt in the denominator. So my dx dt here was 2t, right? And that adjusts it. Remember, when you're doing a second derivative, you always have to do that adjustment. You want d squared y dx squared, not d squared y dx dt. So you have to make sure it's in terms of x both times, even though you took the derivative with return in terms of t. So you got to do that little adjustment at the end. Okay. I'm going to clear this. I have some more room to write. Okay. Next question. At what point is the tangent line to the curve horizontal? Well, let me get my derivative back that I wish I hadn't erased. Okay. So my dy dt, that was 2 cosine t over 2t, right? dy dt over dx dt, right? So that simplifies to cosine t over t. So if I want to know when it has a horizontal tangent, I need to know when the cosine t over t equals 0. In other words, I need to know when the cosine of t equals 0, right? Okay, because that would make the numerator of this thing 0. Okay, so the cosine of t, when is that going to be 0, right? Well, let's draw our little unit circle, shall we? I'm on the interval between 0 and pi. And I need to know when on that interval is cosine going to be 0, right? Well, cosine is your x-coordinate, so that's going to happen up here at pi over 2. Again, I'm only interested in this interval between 0 and pi because that's the only interval they gave me. So this is going to happen when time is pi over 2. Now, to find out what point that is, I've got to put my pi over 2 back up into here, right? So that's going to happen when x is equal to pi squared over 4 minus 5, which is around 2.5. And it's going to happen when y is equal to 2 sine pi over 2, which is just equal to 2. So if we go over here, around negative 2.5 up to 2, and look at that. Boom. Horizontal tangent line. Okay, I can do the same thing if I'm looking for a vertical tangent. The only thing I have to do is take my same derivative and say, well, when is the denominator going to be 0, right? That's going to give me a vertical tangent. So that's a pretty easy one. It's going to happen when t is equal to 0, right? So that's when x is equal to 0 squared minus 5, or negative 5, and y is equal to 2 sine 0. So that is going to be negative 5, 0. Look at that, vertical tangent. And notice there aren't any other ones anywhere in here. This found them all for us. Okay, so this is pretty common that they ask for. There's not a whole lot that they ask us to do with parametrics and vectors, but horizontal, vertical tangents, derivatives, stuff like that is pretty much the basic stuff. Okay, so next video we will talk about polars and polar graphs. We will not do anything with this teddy bear other than appreciate him for the comfort that he is as we head into the AP exam. Okay, any questions about parametrics, pop them in the end of the video, and we will see you soon.